Hello everyone. So I thought I would create this little video to accompany the email that I sent earlier so that if you have additional questions or if you don't quite grasp all these weird things about conversion, scaling, etc. So maybe with the video things would be a little bit clearer. So when you in Huygens, when you finish a deconvolution, you end up with a file that, regardless of what the original depth or type of data was fed into Huygens, it comes back out of the convolution as what is called a 32-bit floating data type. So if you click on your image, so this has just come out of the convolution. If you go and look, usually on the right-hand side panel, you see this histogram. The histogram, as you can see, starts at 0, and for each of the channel goes to around 500 for the blue, around 2000 for the red, and around 6000 for the green. If you click on Statistic tab here, you will see that this is actually a 32-bit float type of data. Okay. The problem that we are experiencing at the moment with the current versions of Huygens is that if each of the channels in this image saved as TIFF results in a TIFF that is more than 1 gig of space required on the disk, somehow it saves as a black empty image. To bypass that, of course, we found the solution that we can save as ICS file, which is very handy because it saves as 32-bit float as well. So if you save your ICS, your deconvolved image as an ICS file, then you can reopen it with Huygens and it will still be the exact same depth and the exact same thing as what it was coming out of the convolution. No sacrifice, no compromise. A very important advantage of this method is that ICS files are extremely quick to save and write, and data loads and saves really quickly with this, so it's very appreciable. But when you actually use ICS, the fact that it's 32-bit makes it twice as big as a 16-bit. It can be a problem for images that are already a problem because they are big. So saved in ICS, they are twice as big. So some softwares are actually struggling to handle this type of data. Imaris is one of them. I noticed a massive difference opening the same image in 16-bit and 32-bit. It's not the same world. Like, it really struggles when you change zoom, especially when you zoom in and the software starts to access a higher resolution image to display because it's a pyramidal display system. In 32-bit, it really takes a long time and it makes the whole experience much more laggy and much more annoying. And for not any real benefit, because the definition of your histogram is not better. It could be better, but in practice, it never really is. It's therefore quite annoying. So to bypass that, it's still interesting to save your deconvolved files as 16-bit. The problem is that if it's a big file, it fails. So in order for Huygens to manage systematically to save 32-bit float in 16-bit, what you will need to do is basically you can right-click on your image and go directly to Operation Window here. Operations window will open an additional window that allows you to basically do an immense number of different operations on your image. The one that we will need is in convert and then data and channel type. When you do that, you see that the right-hand side changes, and by default, it depends what the last selection was. but I think it can be 32-bit float by default, if I'm not mistaken. So what you would want to do is change the basic data type from there to signed integer if you want to scale your image. If you don't want to touch anything to the histogram intensities, then unsigned integer is fine. But signed integer will allow you to prompt the message where you can select whether you want to rescale your histogram. The channel configuration, leave it on stacked. You can also put it on packed. The difference is really not important, to be honest. So usually it is stacked that is being used widely in most configurations. So stick with stacked. So once you have signed integer and stacked, you can actually run your command, and you will see that it's almost instantaneous. This has been changed already and it's ready here. So you can close your window. Remember that actually if you click on your main window, the operation window is still there, and that can be a problem when you do a lot of images and you reopen an operation window every time. That can actually become quite messy. So it's better to just close your window really. Now, if we go back to this, and we look at the type of data that we have, now we have a 16-bit signed integer, not a 32-bit float anymore. That will allow you to actually go right-click, save as, for example, and you can save as 16-bit TIFF. And when you do that, if you save as one per channel, usually it's easier. You give it some destination. Somewhere, test one, whatever, and go OK, and that will prompt you this question about the select conversion mode. Okay, so what I'm going to do is try to demonstrate quickly the difference. I will probably accelerate the video at this point because nobody wants to watch loading screens for half an hour. Because this is a fairly big file, so the saving and opening will be a bit of a struggle. But I will show you the result of contrast, scaled, and clipped in a minute. So I go for this file as 16-bit TIFF. With the three different modalities. So first modality is stretched, second is scaled, and third is clipped. As you can see here, they are all 16-bit unsigned integer. Okay, so they are all the same type. Now, if you actually look at the histogram now, we will see massive differences. So this is the original histogram. You can see that the blue stops at around tips at around 500, the red 2000, and the green at 6000. In the stretched mode, all those channels have been stretched up to the maximum depth in 16-bit being 65,000 and bananas, and you can see that this is where it goes. So it basically extends each of the histograms for all the different channels to the maximum. This has an interesting property when you actually do not care about neither the absolute nor the relative intensities of your different channels, because that gives you a little bit more leeway when you use a software like Imaris, for example, to create your thresholds. You will have a little bit more spread out data, so you will have a little bit more stringency, let's say, in where you put your thresholds, and this will allow you to discriminate structures a little bit more easily. So that's for stretched. Now the scaled option, as you can see, is still another thing. The green reaches up to 65,000, but the others do not reach that far. So the idea of the linked scale is that it takes the brightest original channel. In this case, it was the green that peaked at around 6,000, and it stretched it tenfold roughly until it reaches 65,000. And whatever multiplication factor is applied to the brightest channel will also be applied to the other channels proportionally. So in the end, if this is multiplied by about 10, we can see that probably the blue channel that is around 500 now, or 1,000 now, will probably end up around 10,000 in the scaled version. And this is where we are. So this is 20,000. So this is about 10,000. So that's what happened. So this is the alternative to the stretched option, where you want to keep the relative intensity between your channels still valid. So you still want to be able to measure intensities, for example, in your green and your blue channels that are that make sense in regard to each other. You still want to be able to know that the pixel contained in the object that you created with your red channel are roughly twice as bright as the pixels contained in the object created based on a blue channel, for example. Now, the third and last option is clipped. And as you can see, if you compare the histogram of the clipped option, compare that to the original, it hasn't moved at all. That's the idea of clipped. It just takes whatever the original value out of the convolution is, doesn't change anything. This is it. And that is when not only the relative intensities between your channels is important, but where you do some quantitative estimation of the signal that you are recording when you acquire images, and therefore you don't want to actually interfere with it. So the rescaling is out of question. You just clip it. Now, interestingly, if you want to clip your image, then when you take your 32-bit floating initially, rather than transforming it into a 16-bit signed integer, you can just transform it into a 16-bit unsigned integer, and that will just effectively bypass the rescaling option. So if we do it rapidly, we go to the option window, we go to convert, we go to data, and here instead of signed, I go unsigned, not unsigned, byte, sorry, unsigned integer. Okay, and we run that. This is done. Now, this guy here, as you can see, is a 16-bit unsigned integer. If I actually save it as a 16-bit TIFF now, since a 16-bit TIFF, regardless of what the original format is always saved as an unsigned integer. That means that your intensity histogram goes from 0 to 65,000. In a signed integer, it goes from minus 32 and bananas to plus 32,000 and bananas. So if we do the same thing and we go unsigned integer, for example, scaled or whatever, unsigned integer, it will actually not ask me anything about it. See, it's already saving. So it hasn't asked me whether I want to stretch, link scale it, or clip it. So that was essentially what I wanted people to realize, the different subtleties around what conversions of data type and saving to 16-bit TIFF involves at the moment with Huygens. The bottom line is, if you are not using software down the line after deconvolving your images, and your images size is not a problem, and the software or the post-processing methods that you're using do not pose a problem with big 32-bit floating type of data, then save to ICS your deconvolved images. It's fine. But if this is a problem, like it is for Imaris reconstructions, for example, then use this method, use the operation window, and transform your 32-bit float in 16-bit TIFF. It will be easier to handle. And if you do that and you want to use some form of rescaling, then you have to save it as a signed integer system before you save it to TIFF. Well, with that, thank you for your attention. Bye-bye.